We're now going to take the information that we have about intermolecular forces and how those affect physical properties of compounds that are pure samples and start thinking about what happens when we actually have mixtures of compounds. So this series of lectures for this week will all focus on solubility and how to apply intermolecular forces to this question of solubility. So let's start with a few definitions. First, mixtures, as we've talked about before, are either going to be homogeneous or heterogeneous. This is that diagram of how we classify matter. So all matter is either a pure substance or a mixture. And while we've spent a lot of time talking about pure substances, either as elements or compounds, now we're going to talk about mixtures, but we're going to focus on only homogeneous mixtures. These are mixtures where they look uniform. Like you can't determine which part of the mixture is one compound versus another. A heterogeneous mixture will look like two separate things together, like the example here of gold or minerals at the bottom of a pan of water, right? You can pick out the solid pieces of gold and you can see the water surrounding it. But in a homogeneous mixture, everything would look uniform, similar to this metal alloy that's shown in the picture here. You can't tell which parts of the metal alloy are one element versus another. So as we talk about solubility and solutions, we are going to be focusing in on homogeneous mixtures. All solutions are homogeneous mixtures. They form by intermolecular forces of attraction between molecules of two or more different compounds. And those intermolecular forces we'll see are going to need to be similar. So a solution is defined as two things coming together at least, a solute and a solvent. Now, this just means we're combining at least two things into one thing, and our solute is going to be whichever one of those substances we have less of. And our solvent is going to be whichever one of those two substances or more that we have the most of. And that's it. So in general, we tend to see a lot of compounds dissolved in water. If you ever heard the phrase, water is the solvent of life, it does really dissolve a lot of things that we interact with in our daily lives or that are part of our biology. And we'll talk about why in a little bit. But when we think about water as a solvent, that means that we have more water around than we have of any of the things that are dissolved in it, forming a solution. And we have a whole other word for these types of solutions. We call them aqueous, and we abbreviate that AQ. Here are a few examples of different types of solutions, and they come in all sorts. And even though we'll focus a lot on ones that are in liquids, solutions can be multiple gases mixed together. Like the air around us, it has mostly nitrogen, but it also has a lot of oxygen and other things like argon and carbon dioxide and water as a gas. And they're all mixed together in a uniform way where you can't pick out like the nitrogen in the room or the oxygen in the room. So it's a solution. We also can think of something like salt water. So salt water will have ions dissolved in water. And so this is showing sodium chloride, which is table salt dissolved in water. And so this is a solid solute and a liquid solvent. And that liquid is water. So this one is actually aqueous. And then we also have another one here. This is another solid in a liquid, but these are both metals. Mercury is actually a liquid at room temperature. And so this is a solid dissolved in a liquid. Or actually, it looks like the solvent is actually the solid. And so you can have different types of phases combined into mixtures that are homogeneous solutions. You can have gases, you can have gases and liquids, you can have liquids and liquids, you can have liquids and solids, you can have solids and solids, all of the different combinations. But we are going to focus in this class on solutions that are in that have a solvent that is a liquid. This is because we're going to spend a lot of time thinking about how to extract cannabinoids and terpenes into a solution of either water or alcohol or oil. And so let's take a little bit of a closer look at liquid solvents. So in general, solutions in the liquid or the solid phase form through intermolecular forces of attraction between molecules of more than one compound. And it's really a similarity of those intermolecular forces that make it easy for these to come together and form a solution. So here is an example of ethanol and water mixing as a solution. So in this case, our ethanol is going to be our solute. In this example, both ethanol and water are liquids, and they are both covalent molecules that are mixing together. And it's their intermolecular forces that are similar enough that they can come together and form this uniform homogeneous mixture. We'll talk more about intermolecular forces in a bit, but what I want to focus on here is that the atoms that are bonded together for each of these molecules aren't changing at all. So the ethanol and how those atoms are arranged to form ethanol stay the same in the solution or in the pure substance. Same with water. It is the same as a pure substance or here in this solution. The only thing that is changing is the intermolecular forces between them. Remember, these aren't covalent bonds. They're about maybe 5 to 10% the strength of a covalent bond. And these molecules, unchanging, are going to tumble all over each other because they're both liquids in this situation. There is another type of solution that forms in the liquid state between an ionic compound and water that is going to actually break apart the bonds. So covalent bonds are going to stay bonded in these solutions, or an aqueous solution, for example. And for ionic compounds, they're either going to dissolve or not dissolve. If they're not dissolving, they'll form a heterogeneous mixture where you'll have a bunch of solid ionic compound at the bottom of like a cup of water. And that's not a solution because it's heterogeneous. We don't have a uniform mixture. So the situation where you actually form a solution with an ionic compound, it means that the ionic bonds between your cation and the anion have broken apart and been replaced with intermolecular force attractions between the solvent and the ions. And this picture is trying to demonstrate that. So unlike what we just saw before, which was two covalent molecules, this is an ionic compound and a covalent compound mixing together. And the ionic compound breaks its ionic bonds, and we will have our negative anions separate from our positive cations and surrounded by the solvent. And so in this situation, we have charged particles distributed throughout that liquid. Whereas with our two covalent molecules, they were neutral. There weren't any charges distributed throughout the liquid, right? And that's going to really affect the behavior of the solution. The one with the ions is going to be able to conduct electricity. And so we'll actually call this an electrolyte. Electrolytes are just solutions that have solutes that form charged particles. This is typically ionic compounds. It's also acids and bases. And they'll conduct electricity across them. So this picture up above is sodium chloride, table salt dissolved in water. And it's an example of a strong electrolyte. A strong electrolyte just means that all of the sodium chloride ionic bonds are going to break apart rather than maybe only half or a third of them. Some compounds like acids and bases may only form a certain percentage of their molecules will form a charged particle when dissolved in water. And so while you're not expected to determine if an acid or a base is going to form an electrolyte, It is important to know that we have these kind of two types of solutions. Some will conduct electricity, some will have ions present in them, and others will not. And we have lots of examples of both of these. And this is going to bring me to my last definition, which is solubility. So solubility, we've talked about solution, which is made up of solute and a solvent. Now, solubility is a measure of the amount of a solute that can dissolve in a given volume to form a solution. So it's really just like, here's the measure of how much of our solute can actually form a uniform mixture in the solvent that we have. So a saturated solution is just going to be something that has the maximum amount of that solute. If I put more of it into the solution, it would just fall to the bottom of the container. An unsaturated solution has less than that maximum amount. So if I added more of the solute in, it would dissolve, it disappear into the kind of uniform solution that we were working with. All right, so that will hopefully give you some definitions for us to start talking about solubility of different compounds and different types of solvents.